Hello everyone. Welcome to today's lecture on engineering mechanics. My name is Alagal Hari Krishna, Assistant Professor, Department of Mechanical Engineering, KSR College of Engineering, Kadapa. In this session, we are going to learn one of the most foundational and practical, powerful concepts in the entire engineering mechanics subject, and the concept is called the center of gravity. Now, let me ask you a simple question before we begin. Have you ever wondered why does a tall bus feel more likely to topper than a sports car? Why does a tight rope walker extend their arms sideways? Why do cranes have those massive concrete blocks at their base? Why does a ship not capsize even in rough waves? The answer to all these questions, every single one is rooted in the concept of center of gravity. So, this is not just a theoretical topic for your examination point of view, and it is a concept that engineers use every single day. So, in the fields of, let us say, automotive design, aircraft loading, structural engineering, marine engineering, and even in biomechanics and robotics. And today's lecture is structured as follows. We will begin with by understanding what exactly the center of gravity is from the first principles, and then we will distinguish it clearly from the two related terms called as center of mass and centroid, which students often confuse. So after that we will derive the mathematical formula for center of gravity and the study of centroid locations of all the shapes you need to know, and learn the step-by-step procedure or tabular method for composite bodies by finding the center of gravity. We will then solve a numerical problem together and finally look at some real-world engineering applications. Let us start from the very beginning, from the first principles. Imagine you are holding a book in your hand. When you let go, it falls down. Why? Because the earth is pulling it. That force is gravity. Now here is a crucial question. Where exactly is gravity acting on that book? Many students will say gravity acts on the book as a whole. But that is not precise enough. The truth is gravity acts on every single particle of that book. Every atom, every molecule inside the book is being pulled downward by the gravitational force of the earth. So in reality, there are millions and millions of tiny gravitational forces acting throughout the entire book of the entire body of the book. Now in engineering analysis, we cannot deal with millions of individual forces. So that would be impossibly complex. So we need a way to replace all these distributed gravitational forces with a single equivalent resultant force. And that is exactly what we do. We find one single point through which a single resultant weight force can act such that its effects on the body is identical to the combined effect of all the individual gravitational forces. That special point is called the center of gravity, and it is abbreviated as an CG. So the formal definition is the center of gravity is the point at which the entire weight of the body may be assumed to be concentrated and through which the resultant gravitational force acts regardless of the orientation of the body. Now let me highlight the three extremely important properties of CG that you must remember. The property one is, if you support a body exactly at its center of gravity, the body will be in perfect equilibrium. It will be balanced in any orientation you place it. This is because the weight has no net moment about the center of gravity. So there is no tendency to rotate. And second property is the center of gravity does not have to lie inside the physical material of the body. For example, consider a ring, a hollow circular ring. its center of gravity lies at a geometric center, right in the middle of the empty hole, where there is no material at all. Similarly, for L-shaped section or U-shaped section, the center of gravity often falls in the empty space. We will see this in our numerical problem. And the property number 3 is, for a body in a uniform gravitational field, which is a standard assumption we make near the Earth's surface. So the center of gravity remains fixed related to the body, regardless of how you orient or move it. Now look at the seesaw diagram on this side. A seesaw balances perfectly when the pivot point is exactly at the center of gravity of the combined system. The system of children's plus the plank. The child on the left exerts a clockwise movement about the pivot, and the child on the right side exerts an anti-clockwise movement. When balanced, these movements are equal, and that the balance is the center of gravity. This is the physical institution behind the center of gravity concept. So it is the balance point of weight distribution. So to summarize this slide, center of gravity is the point where the resultant of all distributed gravitational force acts. It is a single fixed point that represents the effective location of the body's entire weight. Now in your textbooks in engineering practice, you will encounter 3 closely related terms: center of gravity, center of mass, and centroid. These 3 terms are often used interchangeably, and that causes a lot of confusion among the students. So let me now draw a clear distinction between all these 3. Let us start with the center of gravity. The center of gravity is fundamentally a mechanical concept. It depends upon the gravitational field. So it is the point through which the resultant force acts. Now the weight is not just about how much matter is present. It is about how much gravitational pull the earth exerts. So if the gravitational field is not uniform, for example, if you have a very large body where the gravity at the top is slightly less than at the bottom, the center of gravity and the center of mass will not coincide exactly. For all the practical engineering applications near the Earth's surface, we treat gravity as a uniform. So this difference is ignored. The center of gravity depends upon the both mass distribution and the gravitational field. Now the center of mass. The center of mass is a purely mechanical concept based off mass distribution alone. It has absolutely nothing to do with the gravity. So if you are designing a satellite orbiting in space where there is microgravity, the satellite still has a center of mass. The center of mass is the weighted average position of all the mass in the entire body. It is the point that moves as if all the mass were concentrated there when a force is applied. For uniform gravitational field, which we always assumed in the standard engineering problems, the center of mass and the center of gravity coincide exactly. So in your examination, you can treat them as same point. Now the centroid. The centroid is a purely geometrical concept. It has nothing to do with gravity and nothing to do with mass. It is simply the geometrical center of a shape. Whether the shape is a line or area or volume, whatever it may be, the centroid is calculated based on purely on the geometry. So it is the average position of all the points in that geometrical shape. Then when does the centroid equal the center of gravity? Only when 2 conditions are met. The first one is the gravitational fields must be uniform, and the second one is the material of the body must be homogeneous, meaning it has the same density throughout. If the density varies from one part of the body to another part of the body, like a composite beam with steel on the top, concrete at the bottom, and the centroid of that cross section is not the same as the center of gravity of the beam. So to summarize the comparison clearly, center of gravity depends upon the gravity and the mass distribution used in static problems. And then center of mass, it is depends only on the mass distribution used in dynamics and shape mechanism. And then centroid, it depends only on the geometry used for homogeneous bodies and uniform gravity. And the key result that you will use in 90% of your engineering problems. So for a homogeneous body in a uniform gravitational field, the center of gravity equals to center of mass, that equals to centroid, all are equal. So this is the working assumption in all engineering mechanics problems. So remember this distinction. It will save you from conceptual errors in both the theory and numerical problems. Now let us derive the mathematical formula for the center of gravity. This is where we move from intuition to calculation. Pay close attention. The derivation is very simple but extremely important. So consider a rigid body of total weight W. This body is made up of a very large number of small elemental particles. Let the I particle have weight Wi and be located at position coordinates like xi, yi, zi with respect to chosen reference frame, and that is our x and y z axis. Now we apply the principle of moments, which is very important and one of the most powerful principles in engineering mechanics. And it states that the moment of the resultant force about any axis is equal to the sum of the moments of all the individual forces about the same axis. Let the CG be located at coordinates x bar, y bar and z bar. The resultant weight W acts through this point only. Now taking moments about yz plane, that is about the y and z axis, we get so x into x bar, W into x bar equals to W1 into x1 plus W2 into x2 plus W3 into x3, so plus and so on. That itself equals to the algebraic sum of Wi and xi. And therefore x bar equals to sigma Wi into xi divided by sigma W. Similarly, taking moments about the xz plane, that is nothing but your y bar. That is similarly we can get the same equation, but sigma Wi into yi divided by sigma W. So and about the xy plane, z bar equals to sigma Wi into zi divided by sigma W. So therefore the three coordinate equations for the center of gravity in vector form we can write as r bar, that equals to sigma Wi into ri divided by W, sigma W, where the r bar is the position vector of the center of gravity. Now for engineering problems involving areas, uniform thin plates where we assume uniform thickness and uniform density, the weight of each elementary particle is proportional to its area. So Wi equals to rho into T into G into AI, where rho is the density, T is the thickness, G is the gravity, and AI is the elemental area. Since rho, T and G are the constant for the homogeneous plate, they cancel out from numerator and denominator, and the formula simplifies to x bar equals to sigma AI into xi divided by sigma AI. Y bar equals to sigma AI divided by sigma AI. So this is the centroid formula for areas, and that is what we will see in almost all 2D problems. The quantities AI and XI and AI and YA are called the first moments of area about the y-axis and x-axis respectively. For continuous bodies where we cannot discretize into finite particles, we use the integral form, that equals to x bar equals to integral x dA divided by integral dA, y bar equals to integral y dA by integral dA. This integral form is used when deriving the centroid of curved shapes like semicircles and parabolic areas from the first principles. Now let me give you the physical meaning of this formula. X bar is simply the weighted average of the x coordinates of all the area elements. where the weights are the areas of each element. So think of it as finding the balance point of that area distribution along the x-axis. This is exactly the same idea as finding the average score of a class. But here instead of scores we have positions, and instead of a number of students we have areas. And we observed three important things to noted about this formula. The first is, you need a clearly defined reference axis. So the value of x bar, the value of y bar will change depending upon where you place your origin. So always define your reference axis clearly at the starting itself. Secondly, the formula works for any shape, no matter how complex, as long as you can break into parts whose centroids you know. And the third, for cutouts or holes, you use a negative area. We will see this in the composite body method in the next slide. And this formula is the backbone of all centroid and CG calculations. So master it completely. Before we can apply the composite body method to complex shapes, we need to build our toolkit. We need to know by heart the centroid locations of the most common standard shapes, and these are the building blocks from which complex shapes are assembled. Let me go through every one carefully, and I want to use not just memorize the results. So I want to understand why each centroid is where it is. If you consider the shape one, that is a rectangle, it is having width b, height h, and this is the simplest case. A rectangle has two axes of symmetry, the horizontal center line and the vertical center line. The centroid always lies at the intersection of axis of the symmetry. So the centroid of a rectangle is at x bar equals to b by 2 from the left edge, and y bar equals to h by 2 from the bottom edge, and we know that area equals to b into h. Simple, symmetric, straightforward. If your reference is at the bottom left corner, the centroid is at the midpoint. Let us consider the shape 2 as there is a triangle. It is having a base b and height h. The centroid of the triangle is not at the midpoint of the height. That is the common mistake most of the students will do. The centroid of a triangle lies at the 1/3 of the height from the base, or equivalent to 2/3 from the apex. So y bar equals to h by 3 from the base along the x-axis. If the base is horizontal, x bar depends upon the shape of the triangle. So for a right triangle with the right angle at the at the origin, x bar equals to b by 3 from the right angle vertex, and the area equals to half bh. And remember, the centroid of the triangle is where the three medians intersect. It is called a centroid in geometry as well. And now move to the third shape, circle, which is having a radius small r. A circle has an infinite axis of symmetry. They all pass through the geometrical center. Therefore, the centroid of a full circle is at its center. So x bar equals to 0, y bar equals to 0. So if the origin is at the center, and we know that the circle area is pi r square. This is trivially simple because of the perfect symmetry. Now the another shape is called fourth shape, a semicircle, is also having the radius small r. A semicircle has only one axis of symmetry, the vertical axis through the center. So x bar equals to 0 along the axis of symmetry, but y bar is not at r by 2. It is not at the midpoint of the radius. Due to the curved shape, more area is concentrated near the flat edge than the near top. The centroid is actually at y bar, that equals to 4r by 3 pi, measured from the diameter edge, let us say the flat edge. So let me compute this numerically. 4 divided by 3 into 3.14, that is a pi value. So finally it is becomes as 0.4244 r. So y bar equals to 0.424 r from the flat edge. So as you know, area equals to pi r square by 2. The results comes from integrating YDA over the semicircular area, and it is a standard result you must memorize. So next, the last another shape is a quarter circle, which is also having the radius r. A quarter circle has no axis of symmetry. That means by assuming the two straight edges are along the axis. By integration, x bar equals to y bar equals to 4r by 3 pi, which means 0.424r from both the straight edges. And notice that this is the same numerical value as the semicircle's y bar. That makes sense due to symmetry of the quarter circle about a 40-degree line. Now let me give you a very useful tip. Whenever a shape has an axis of symmetry, the centroid always lie on that axis. You can use this to immediately determine one coordinate of the centroid without any calculation. For example, a rectangle has two axes of symmetry, so that the centroid is immediately known to be at this intersection. A semicircle has one of the symmetries, so x bar equals to 0 automatically. A circle has the center as its centroid. So this symmetry principle saves enormous effort. So also remember, for composite problems, all coordinates must be measured from the same reference origin. So don't mix up reference points between the different parts, and that is one common errors that student will commit. So memorize all 5 of these shapes with their centroid locations and area formulas. So in the next slides, we will combine them using composite body method. Now we arrive at the most practically important skill in the entire topic, the method to find the center of gravity of composite bodies. In real engineering, almost no cross section or shape is a simple rectangle or circle. So structural problems have I sections, T sections, L sections, C sections, and mission parts have holes, flanges, cutouts. This is where the composite body method becomes your most powerful tool. This method is based on the simple but powerful idea. So any complex shape can be built up from or subtracted from a combination of simple standard shapes whose centroids we already know. Once we have the individual centroids, we use the weighted average formula to find the overall centroid. Let me walk you through the 5 steps in detail. So the first step is divide the body into simple parts. So look at your complex shape and identify how to break into rectangles, triangles, semicircles, quarter circles, or any combination of standard shapes. There is no single correct way to divide. Choose a division that gives you the simplest parts. Sometimes it is better to think of a complex shape as a larger simple shape minus a smaller cutout. For example, I section can be treated as a large rectangle minus 2 smaller rectangles cut from the sides. So when you have a hole, a circular hole punched out of your plate, for instance, you treat that hole as a negative area. That material is absent there. So its contribution to the moment sum is abstracted. Come to the next step, establish a reference coordinate system. So choose your reference origin carefully. This is the point from which you will measure all xy distances. The most common choice is the bottom left corner of the overall bounding rectangle. Sometimes it is more convenient to choose the centroidal axis of one of the parts or the axis of symmetry of the composite shape. Whatever you choose, be consistent. So every single centroid coordinate system in your table must be measured from the same reference point. Never mix the reference points between the parts. So it leads to confusion. And coming to the third step, locate the centroid of each individual part. For each part, you identify in step 1, determine its area AI, positive for solid regions, negative for holes or cutouts, and then centroid coordinates x bar I and y bar I, measure from the chosen reference origin. So use the standard shape formulas from the previous slide and draw the shape carefully. label all the dimensions, and compute the centroid coordinates systematically. So for a rectangle, the centroid is at its geometric center. For a triangle, it is at h by 3 from the base. And the fourth step is construct the tabular calculation. This is where engineering discipline comes in. So set up a neat table with following columns: part number, area A with a sign negative for holes, x bar I, centroid x coordinate from the reference, y bar I, centroid y coordinate from the reference. So a bar into x bar I for first moment of area about y axis, ai into y bar I first moment of area about y axis. So fill in all rows, then compute the totals at the bottom. So total area equal to sigma ai, and total ai into x bar I equals to sigma ai into x bar I. Total ai y bar I equal to sigma ai total ai y bar I. So this tabular method is organized, easy to check. So we can minimize the errors also. So in your examinations, so always present a solution in this good tabular format. It shows clear methodology and earns full marks even if you make a small arithmetic error. So the last step is apply the centroid formula. Now simply divide x bar equals to sigma ai x bar I divided by sigma ai. So y bar equals to sigma ai y bar I divided by sigma ai. So these two results give you the coordinates of the centroid of the composite section measured from your chosen reference origin. So important note from this step is, if the shape has an axis of symmetry, the centroid lies on that axis. So you can use this to verify your answer. So sigma a, suppose if sigma a is equal to 0, so which can happen for a wireframe or purely subtractive shape, and the formula breaks down, but this is extremely rare in the standard problems. So your final answer must be always state that coordinates clearly. The centroid is located at x bar, that equals to some mm from reference, and y bar equals to some mm from reference. And this method, divide, tabulate, compute, is a systematic, reliable, and applicable to any shape, no matter how it complex. In the next slide, we will apply this method to a complete numerical problem. Now let us apply everything we have learned so far to a complete step-by-step numerical problem. Follow along carefully. This is the type of problem that will appear in your university examinations. So the problem statement is: find the centroid of an L-shaped cross section. The section consists of a vertical flange that is 20 mm wide and 80 mm tall, and a horizontal flange that is 60 mm wide and 20 mm tall. The two flanges share the bottom left corner. Let us solve this systematically using a 5-step composite body method that we discussed just now in the previous slide. So here the step 1 is divide the shape. The L section shape can be easily divided into two rectangles. There are with the two parts. So part 1 and part 2. The part 1 is vertical rectangle 20 mm wide and 80 mm tall. The upper portion of the upright portion of the L. And by considering the second part, that is horizontal rectangle 60 mm wide and 20 mm tall. And there is nothing but the base portion of the L. So you should note one thing here. You could also think of it as a large 80 by 80 rectangle minus two pieces, but the two rectangle approach is simpler here. Then the step 2 is establish reference axis. As we discussed in the previous slide, we place our reference origin at the bottom left corner of L section. The axis runs horizontally to the right, and the y-axis runs vertically upward. All the measurements will be made from this origin. And step 3, find the centroid of each and every part. So for part 1, the vertical rectangle, that is 20 mm by 80 mm. So the area is 1600 mm square. The centroid of this rectangle is its geometric center. X bar 1 equals to 20 by 2, that equals to 10 mm from the left edge, because that is the reference origin. So y bar 1 equals to 80 by, that equals to 40 mm from the bottom edge from our reference origin. Similarly, if you consider that for part 2, horizontal rectangle, that is 60 by 20 mm. area 1200 mm square. The centroid of this rectangle is at a geometric center. So x bar 2 equals to this rectangle start at x equals to 0, that is extreme left edge of the L shape, and extends to x equals to 60 mm. So its centroid x coordinate is 60 by 2, that equals to 30 mm from the left edge. But since its left edge is at x equals to 0 of our reference, x bar 2 equals to 30 mm. Let me re-examine this. The horizontal flange of the L section, does it start from x equals to 0? If the vertical flange occupies 0 to 20 mm in x, and the horizontal flange extends from x equals to 0 to x equals to 60 mm at the bottom, let me examine that. Yes, x bar 2 equals to 30 mm from the reference. But let me reconsider, the classic L section has the horizontal flange starting x equals to 0 on the left, extending 60 mm to right, and occupying y equals to 0 to y equals to 20 mm in height. So for part 2, x bar 2 equals to 60 by 2, that equals to 30 mm. However, in our table, we have x bar 2 equals to 50 mm. This would be the case if the horizontal flange starts at x equals to 20 mm. That means it starts where the vertical flange ends. Let me clarify both interpretations and use the values shown in our table. X bar 2 equals to 50 mm, y bar 2 equals to 10 mm. This corresponds to horizontal flange running from x equals to 20 and y equals to 80, centered at x equals to 50. Y bar 2 equals to the horizontal rectangle occupies y equals to 0 to y 20 mm, right? Yes, y 20 mm. So its centroid is at 20 by 2, that equals to 10 mm from the bottom. So y bar 2 equals to 10 mm. And step 4, where we discussed it in the previous slide, that is the tabulate the calculations. Now we build our calculation table. Part 1, A1 equals to 1600 mm square, X bar 1 equals to 10 mm, Y bar 1 equals to 40 mm. A1 by X bar 1 equals to 1600 by 10 equals to 1600 mm cube. So A1 equals to A1 into Y bar 1 equals to 1600 into 40, that equals to 64,000 mm cube. For part 2, the A2 is 1200 mm square, X bar 2 equals 50 mm, Y bar 2 equals to 10 mm. Similarly, A2 X bar 2 equals to 60,000 mm cube, A2 Y bar equals to 12,000 mm cube. If you observe the total things, the sigma AI equals to 2800 mm square. Similarly, sigma A into X bar I equals to, so here we are having 16,000 and 60,000, and the total is 76,000 mm cube. Similarly, sigma AI Y bar I equals to 64,000 plus 12,000, that equals to 76,000. So and then apply the formula, as we know that X bar equal to sigma AI X bar I by sigma AI. So we can get 27.14 mm, and also Y bar equal to sigma AI Y bar I divided by sigma AI. So we will get 27.14. And from the observation from this table, what we conclude is a centroid of L section is located at X bar equals to 27.14 mm and Y bar equals to 27.14 mm from the bottom left reference corner. Now this is the most interesting part of this result. Look at the diagram on the left. The centroid is at 27.14, 27.14. If you plot this point on the L section, you will find that it falls in the empty space inside the L section, not on any solid material. This beautifully confirms what we said earlier, the center of gravity or centroid so does not have its lie within the physical material of the body. So also notice an interesting coincidence in this particular problem, X bar equals to Y bar. This makes sense due to the symmetric way the L section is constructed here. So when you want to verify at the end, the centroid must be lie within the bounding boxes of the shape. In this case, within 80 by 80 bounding square. So our answer is 27.14, comma 27.14. So satisfies this. So also do a sanity check your final answer. Now that we have mastered the mathematics and the method, let us step back and appreciate why center of gravity is so fundamentally important in engineering practice. The concept we have studied is not just an academic exercise, it is a design parameter that engineers must carefully control the virtually every field of engineering. So let me take you through 6 important domains. So the 6 important domains are automotive engineering, aerospace, structural engineering, marine, biomechanics, and manufacturing. Let us consider the first application. So automotive engineering. So have you ever noticed that sports cars are very low and wide, while trucks and SUVs are taller and very narrower? This is directly related to the center of gravity. A vehicle is stable against rollover as long as the vertical line through its center of gravity falls within the wheelbase. So here the wheelbase is nothing but the area between the 2 contact points of its tires. So if the vehicle leans in a curve, the center of gravity shifts, and if the vertical through the center of gravity falls outside the wheelbase, the vehicle tips over. Racing cars are designed with an extremely low center of gravity, often just a few centimeters above the ground. By placing the engine low, so using flat aerodynamics bodies and using a heavier components near the floor, this dramatically improves cornering stability. So in contrast, in SUV vehicles with a high center of gravity is much more prone to rolling over the sharp turns. So automotive engineers spend enormous effort calculating and physically testing the center of gravity of every new vehicle design. So, and then coming to this second application, aerospace engineering. So every aircraft has a defined center of gravity envelope, a range of allowable center of gravity positions. If the center of gravity is too far forward, the aircraft nose dives and the pilot needs to pull back constantly on the controls. If the center of gravity is too far aft, the aircraft becomes statically unstable. So before every commercial flight, the loadmaster calculates the center of gravity based on the passenger distribution, cargo placements, and the fuel load. Passengers are not seated randomly; they are strategically distributed to keep the center of gravity within the limits. So this is why airlines have specific rules about where heavy cargo goes in the hold. Coming to the third application, structural and civil engineering. In structural engineering, the center of gravity of the cross section is essential, very important for calculating the bending stresses and shear flows and deflections. And wherever the beam is loaded, it bends above that central axis. The axis passing through the centroid of its cross section. The distance from the centroid to the extreme fiber determines the maximum bending stress. For cranes, the center of gravity of the lifted load must remain within the crane's stability, so envelope at all times. So if the crane swings a heavy load too far from the mast, the center of gravity of the crane load system moves outside the support base and the crane tips over. A catastrophic failure. So crane manufacturers provide load charts that define maximum loads at various radii to prevent this. Now next move to the another application, marine engineering. Ship stability is entirely governed by the relationship between the center of gravity and the metacenter. So when a ship tilts, that is what called heeling, the shape of the submerged volume changes, shifting the center of buoyancy. The metacenter is the point where the line of action of the buoyancy force intersect the ship's center line. So for the ship to be stable, the above metacenter must be above the center of gravity. If the center of gravity rises above the metacenter due to loading heavy cargo higher, the ship will be capsized. To control the center of gravity, ships use ballast tanks. large tanks that can fill it with or emptied of seawater. By adjusting the ballast, the ship's engineers can raise or lower the center of gravity, also correct a list, sideways tilts. This is the real-time continuous engineering operation. And then if you consider the another application that is called biomechanics. So the human body center of gravity is located approximately at the level of second sacral vertebra. So which corresponds roughly to the navel region when standing in an anatomical position. So however, the center of gravity shifts dramatically as you move. When you raise your arms, the center of gravity move upwards. When you bend forward, it shifts towards and can even move outside your body. So athletic performance heavily depends upon the center of gravity manipulation. A high jumper using the Fosbury flop technique arches their back in such a way that the center of gravity actually passes below the bar. So the body goes over the bar while the center of gravity goes under it. This is a brilliant use of CG mechanics. Similarly, sprinters learn forward at the start of their center of gravity ahead of their feet. So creating an unstable condition that propels them forward. And last applications that is called manufacturing and material handling. So in manufacturing, knowing the center of gravity of heavy components, engine blocks, turbine rotors, large castings is essential for safe lifting and transportation. So if a crane hook is not positioned over the center of gravity of a heavy component, the component will tilt when lifted. So which can be dangerous now. So manufacturers design, certify specific lifting points on heavy equipment. So position such that the hook force passes through the center of gravity of component. So in summary, center of gravity is not just an examination topic. So it is a live engineering parameter that affects safety, stability, and performance and efficiency across every branch of engineering. So it is very important to learn about the center of gravity. So let me see in this slide the summary and the key takeaways. So we have covered a tremendous amount of ground in this lecture. Let me now consolidate everything into 7 key takeaways that I want you remember long after this lecture over. So takeaway 1 is center of gravity, the core concept. The center of gravity is the single point through which the resultant of all the gravitational forces on the body passes. So it is the balance point of the body weights distribution. Any body supported at its center of gravity will be in perfect equilibrium in any orientation. This is the most fundamental result of this entire topic. So takeaway 2, the three-way equality for a homogeneous body. So one with uniform density throughout, subjected to a uniform gravitational field, which is our standard assumption. The center of gravity, the center of mass, and the centroids are the same point. So in 99% of your engineering mechanics problems, you will use this equality. The distinction between these 3 concepts matters only in advanced problems involving some non-uniform gravity or non-homogeneous materials. And third one is the weighted average formula. The formula for the center of gravity is weighted average. So x bar equals to sigma ai into y bar I divided by sigma ai. This comes directly from the principle of moments. Understand this derivation. Don't just memorize the formula. So the physical meaning is the center of gravity is the area weighted average position of all the parts of the body. So the point number 4 is the composite body method. So here we observed 5 steps. For any complex shape, we have to divide into standard parts, set up the reference axis, find the individual centroids, and the fourth step is so tablet a and x bar I and y bar I, a x bar and a y bar values, and it becomes very easy to observe. So and fifth one is apply the formula. And if you follow this standard step-by-step form and method, this systematic approach is the correct way to solve any centroid problem in your examinations. So always present your solution in this format. So it gives you a good impression. So now point number 5 is negative areas for holes and cutouts. Yes, when a shape has a hole, cutout or void, or treat it as a standard shape with a negative area. So subtract its moment contribution from the total. So this is an elegant application of superposition principle. So the complex shape equals to simple complete shape minus the removed portion. So and then next takeaway is center of gravity can lie outside the body. The center of gravity is not required to lie within the physical material of the body. So for hollow shapes, rings, L sections, U sections and other non-convex shapes, the center of gravity may lie in the empty space. This is not a contradiction. So it simply means that the weighted average position of the material falls in a region where no material is present. So always verify your answer by plotting the center of gravity on your diagram. So the next takeaway is, stability requires yellow center of gravity. So in engineering design, as you understand in the previous set of applications, in engineering design, stability again is tipping, rolling, and capsizing requires the center of gravity to be as low as possible. So if the center of gravity will be high, it is a problem. So this principle governs the design of vehicles, ships, structures and different equipments. The lower the center of gravity relative to support the base, the more stable the system. This is why heavy machinery is always built with heavier components at the base. So before I close, our next topic will be the moment of inertia, so also called the second moment of area. And if the centroid is the first moment concept, the weighted average position area. Then the moment of inertia is the second moment concept. It tells us how the area is distributed about an axis. Moment of inertia governs bending stiffness, rotational dynamics, beam strength, etc. etc. It goes directly on what we learned today. So about the centroidal axis. So I hope this lecture has given you not just the calculation technique but a deep understanding of center of gravity. Thank you all for your attention.